Welcome everybody. Today I'll be presenting the first physics paper of the year, and it's an important discovery in modern physics. It's on the first direct detection of gravitational waves. The paper is titled Observation of Gravitational Waves from a Binary Black Hole Merger by Abbott et al. This paper is a bit old, published in 2016, but it has a profound impact, which is why I chose it. In my presentation, hopefully I can explain what was detected, how the detection worked, and why this result changed astronomy and physics in a way that makes sense to everybody here. All right. Two black holes, 1.3 billion light years away, are in delicate equilibrium, orbiting around each other carefully, when suddenly disaster strikes. What happens? What happened? We don't know, but their orbits are converging, gaining speed. An unstoppable force pulling them in. And then they collide. In that moment, their energy eclipses all the rest of the observable universe's stars, becoming the most powerful entity. And somehow we detected it. But not in the way you'd expect, like a shockwave ripping through Earth's crust. No, this was something far more mysterious. A distortion in LIGO, smaller than 1,000th the width of a proton. What? Stay with me to unlock the secrets of the universe through this paper. All right, to understand this paper, here's some key terms that we first need to know. I'm going to introduce 6 terms, which may sound like jargon at first, but if you stick with me, you will gain a solid understanding of this paper and the terms. First, gravitational waves. These are ripples in space-time itself. They're created when massive objects, like black holes, accelerate, and these waves propagate out at the speed of light. This can be hard to conceptualize, even for the physics people here. So you can think of it like analogous to electromagnetic waves, which are created by accelerating charges, but that's not too helpful either. I find it's a more helpful way to conceptualize is if we envision space as a kind of calm pond, then dropping a rock in would send out reverberating ripples that disrupt the surrounding environment itself. And that's a good way to kind of look at what a gravitational wave is if we kind of extrapolate that into 3D and add the dimension of time. Next is strain, which is what our sensors are actually measuring in this paper. Denoted lowercase h is the fractional change in length, delta L over L. And basically this just means that if an object's length is being distorted, then we can measure how much it is by how much its change in length is over the total length. It's a direct product of gravitational waves, which makes sense, since ripples in space itself naturally lead to distortions in object lengths. Next is chirp mass. So, wait, why is there an image? Is that something? Okay, I don't know, I think that's from the TV. But anyhow. So this is a specific combination of the two black hole masses that can be extracted directly from the waveform. It's called chirp mass because it's determined by how the frequency changes and how the frequency and amplitude increase at the same time, kind of like a bird's chirp. We can't figure out, basically M1 and M2 are the two black hole masses. We can't figure out that directly from the strain data, but we can figure out chirp mass quite easily. And by putting some more limitations on our system, we can then solve for M1 and M2. So that's how we actually connect our measurements from the gravitational waves to finally be able to conclude information about the binary black hole system that is so many light years away. So now we've gone through the 3 terms that describe the conceptual and numerical physics of the paper. These next 3 things really describe our observation of the phenomena and how we're measuring data in the first place. First, match filtering. So we need to parse through large amounts of strain data to actually find the relevant signals. So this is basically a searching method. It's essentially pattern matching. So the algorithm computationally computes large amounts. So we have a bunch of predicted waveforms, and we're matching each to the strain data. So it's basically like, you can think of it as trying thousands of keys in a lock. So we don't actually know what the strain data should look like because we don't know what the binary black hole system looks like. But we can predict many possibilities through theoretical physics. And we just try all of them. And when one fits, basically the signal to noise ratio jumps, and we know that we have found a match. Then the merger itself is what we are looking for and what we end up finding, and it has 3 phases. So the in spiral is when the black holes are no longer orbiting in equilibrium, but they're accelerating towards each other. The orbital frequency is kind of increasing, so they basically begin to spiral inwards, hence the name. Second, the merger is when the black holes actually come into contact and collide, releasing a huge amount of energy. And the ring down is an oscillatory phase after they've consolidated into one black hole, and it gradually transfers into a stable state, known as the Kerr black hole. Finally, our experimental setup is called LIGO, for Laser Interferometer Gravitational Wave Observatory, which I'll explain in more detail shortly, the apparatus. And the specific event that we're observing is called GW 150914. Wait, can I? Where's it? Can I remove this? Yeah, remove this. How do I remove this thing? It's like blocking some info. All right. So I know I just threw a lot of information at you. Let's first put these key terms all together, and then we can look at some data from the paper. So this slide kind of shows the logical pipeline of how terms work in the paper. Chronologically, we first observed strain in the LIGO detectors, and we verified that the signal points to something significant via match filtering analysis. Once we know a certain piece of strain data is important, we surmise that the gravitational wave frequency from the strain data, and from the gravitational wave function, the function of the gravitational waves, we can then calculate the chirp mass and then extract M1 and M2, which is the actual information about the binary black hole merger. So this is actually figure 3 in the paper, but I think it's really helpful to introduce the apparatus or the experimental setup before we actually get into the data. So how do we actually measure strain, right? What is LIGO? Basically, LIGO measures strain via these 2 perpendicular 4-kilometer arms that you see in the diagram of the setup. The idea is that passing gravitational waves stretches, a passing gravitational wave will stretch one arm while compressing the other. And we can kind of measure the stretches and compressions of the arms through injected laser pulses from the laser source, magnified through the mirrors, which are called test masses, and then output into the photodetector. And basically, by the time at which a wave can propagate there and back and into the photodetector, we can basically know how much each arm has been distorted. It's actually via a phase shift of the wave, but if we think about it as time propagation of the wave, that's also fine. So, yes. So now we get into searching methods. Why? You might be thinking, why is this important? Why don't we just take the strain data, then just calculate the gravitational waves, and then just conclude data about the actual event of the binary black hole merger? Well, it turns out that this experiment was running for months, and we were basically searching through tons of strain data for months, looking for any gravitational wave disturbance, while the black hole merger that we finally found actually took place over a few seconds. So most of the data that we collect is either instrumental noise or gravitational waves superimposed on the superposition of gravitational waves that's too weak to calculate. So that's exactly why we need to look really hard for these significant signals by implementing good searching algorithms. So we have 2 searching strategies to be as robust as possible. The first is called generic transient search. So basically what this does is it looks for passing gravitational waves without a specific waveform, so it's not looking for matches to a really specific set of parameters about a binary black hole system. Rather, it's just looking for kind of abnormal data or a disturbance that doesn't look like noise that could be something significant. And this is really good because we haven't actually observed any gravitational waves so far, so any comparison that we're doing is basically with analysis. So yeah, this works on poorly modeled sources, and even though we've theorized that these exist, we don't know for sure. So it's good to run this general search with a certain degree of uncertainty. So how this actually works is basically the frequency data about the strain is compared between the two LIGO sites, because the key concept is basically if the two sites discover a signal that's abnormal within a certain time within each other, like if they discover a matching signal within a certain time frame of each other that's abnormal and it matches, then it's probably something significant. They allow for a 15-second window, 15-millisecond window, about 10 milliseconds for the intersite propagation time of gravitational waves between the Washington LIGO site and the Louisiana LIGO site, and an extra 5 milliseconds for just uncertainty in general. So we know that if both detectors see the same unusual pattern at nearly the same time, then we've probably discovered an astrophysical phenomenon, because the same noise won't occur in both the sensors at the same time. That's just because they're not really local to each other. And as you can see in the figure, the detection statistic, which is the signal to noise ratio for the event that we actually detected, is really high, and it has a really low probability of being generated via background noise. And I'll get more into that later. So the second way we search for the event is called binary coalescence search, and this actually assumes that the source of the gravitational waves is a compact binary, like two black holes or two neutron stars, except in the paper we conclude that it can only be two black holes. And using general relativity, scientists can predict what these waveforms should theoretically look like, given a certain set of parameters from a binary black hole system. Then we simply apply match filtering to compare predictions with the real data. So how it's implemented is we generated a search space of 250,000 possible waveforms, and basically we compared each piece of strain data to all of these waveforms, and if we found a match, then that basically means we can extract both data about the we can extract both like data about the event and the physical properties of the black hole system. Again, we have really high detection statistic, we call it rho in this case, for the actual event that we found, and really low probability that it could be anything except like an astrophysical phenomenon. Now let's look at the actual data, like the strain signal and the gravitational wave detected. We've only been looking at searching algorithms and how they found the event so far, but if we look at the actual data, that can give us some insight into how conceptually the gravitational wave works as well. So what we're looking for in the following data is the characteristic chirp, which is increasing frequency and amplitude in the strain data, which is signature of two in-spiraling black holes. So this is figure 1. The left side is the Washington LIGO site, and the right side is Louisiana LIGO site. So we can see that both sites have strain signals spiking at the same time, and their amplitude and frequency are increasing at the same time. So this is kind of typical of a binary black hole system, and it's very unlikely to be noise because they just occur at the exact same time within that 10 to 15 millisecond window of each other. The middle rows, the middle rows actually represent plotting 3 analytical reconstructions against each other, and given the fact that they match so well, they match 94%, it said in the paper, it probably means our conclusion about the binary black hole system was correct, because if we basically conclude data and then plug back into analytical solutions, and it gives the exact same reconstructed wave as we actually detected, then it's no coincidence that we found that black hole system. Here is kind of similar. We compare the waveform reconstructions with the actual template of the observed data. So the numerical relativity is the analytical solution via general relativity, whereas the reconstructed template is after you remove noise from H1. H1 is the Hanford-Washington LIGO detector, the strain signal there. So you can see that they match extremely well again. It's 94% again, actually. And again, notice that they've similarly temporally correlated increases in frequency and amplitude at the same time. So that's going to be exactly what we want to see in a black hole system, in a binary black hole. Yeah, together figures 1 and 2 show that not only do the detectors agree with each other, but the analytical solutions, when we plug back in, also agree with each other, and moreover, the reconstructed analysis kind of agrees with the observed signal. So basically everything just kind of agrees. And so we conclude that it's already extremely unlikely to be a noise. But we can rule out noise even further by seeing the significance in our searching algorithms. So what's basically important here is the background lines show how often at a certain detection statistic it's likely to be background noise, whereas the event is marked GW150914. And we can see that the burst search gives 4.6 sigma significance, meaning that it would only be a coincidence once every 22,000 years, whereas the other search gives 5.1 sigma significance, and it would only be a coincidence once in about 203,000 years. So it's very unlikely to be a coincidence, again. And then just to solidify just to be sure, we have to rule out detector issues and instrumental noise that might have been able to cause the exact same signal. So like if we get really lucky, then maybe seismic activity in the Earth could have caused the same signal. So we have to kind of validate that our signal was not caused by instrumental noise by doing really extensive testing. So they did extensive validation and found that both detectors were operating normally. Environmental sensors, including seismometers, microphones, and magnetometers, showed no disturbances that could have possibly matched the signal. And like signal injection into the instrument showed was unable to recreate the gravitational wave that was observed. So after all these checks, basically no terrestrial explanation or instrumental explanation remained for what we observed, so the only possibility was an astrophysical phenomenon. So we're finally able to confidently conclude the following. So the black holes have 36 and 29 solar masses respectively, and the final consolidated Kerr black hole had 62 solar masses. The last three data points are kind of more esoteric. The spin describes a property unique to the post-ring-down Kerr black hole, as opposed to a Schwarzschild black hole. And the luminosity distance and the redshift are kind of cosmological metrics that measure like a stellar phenomenon's position and velocity relative to Earth. Notice though that the concluded data about the black holes, I mean, though it's important, it's rather unimportant in the grand scheme of things. The true significance and why this paper is actually historic lies in three reasons. First is the detection of gravitational waves for the first time, confirming Einstein's prediction from 100 years ago, and also adding candor to the now revered theory of general relativity. Second, it's the first observation of a binary black hole merger, which is a very powerful phenomenon that we now know exists, that was previously unconfirmed. And third, it marks the birth of gravitational wave astronomy, which is a whole new way to look at the universe, as opposed to electromagnetic astronomy. So, looking ahead, possibilities are kind of endless. Future goals include building more advanced and just more LIGO detectors, so we are able to kind of localize phenomenon better. So triangulation would be possible, and detection of smaller disturbances from other binaries would be possible with more advanced sensors. And predicting trends across the universe with these black hole populations via that's kind of the essence of gravitational wave astronomy itself. And we're able to observe these kind of phenomena that we wouldn't be able to observe before with any other kind of astronomy. And finally, this discovery also helped to focus theoretical physics, especially for people that were trying to unify quantum gravity. Now we know that gravitational waves exist, and we can impose limits on how they function and how gravitons function, so we can come up with a better theory. So yeah, those are the significances. Thank you for listening.
We don't have time for questions. We got to get to classes. So, what's next week?
Not scheduled.
No presentation next week?
There's no journal club presentation next week. Please push in your chairs. And what?